We solve Bode problems. So we'll take an example. Get the Bode plot for the following transfer function and determine phase margin and gain margin. So g of s is equal to 75, 1 plus 0.25 s and divide by s into s square plus 16s plus 100. Solution: on comparing the quadratic factor of the denominator g of s with the standard form of quadratic factor, we can estimate that s square plus 16s plus 100 is equal to s square plus 2 zeta omega ns plus omega n square. By comparing, we'll get omega n square is equal to 100 and omega is equal to 10, and 2 zeta omega n is equal to 16. Zeta is equal to 16 by 2 omega n is equal to 16 divided by 2 into 10, that is 0.8. Let us convert the given S domain transfer function into Bode form or time constant form. G of s is equal to 75 into 1 plus 0.2s divided by s into s square plus 16s plus 100. So 75 into 1 plus 0.25 s divided by s into 100. S square by 100 plus 16 by 100 plus 1. So 0.75 into 1 plus 0.2s s into 1 plus 0.01 into s square plus 0.16 into s. The sinusoidal transfer function g of j omega is obtained by replacing s by j omega in g of s. So g of j omega is equal to 0.75 1 plus 0.2 j omega divided by j omega 1 plus 0.01 j omega square plus 0.16 j omega. So if you simplify the equation, we'll get 0.75 1 plus j 0.2 omega divided by j omega 1 minus 0.01 omega square plus j 0.16 omega. So the corner magnitude plot, the corner frequencies are omega c1 is equal to zero point 0.2 is equal to 5 radians per second and omega c2 is equal to 10 radians per second. So first one is point, you can see in the diagram, that is 0.75 by j omega. The corner frequency, corner frequency, so slope is minus 20 because j omega is in denominator, minus 20. So the change in slope decibels is nil. So next one is 1 plus, you can see the diagram, numerator part 1 plus j 0.2 omega. That the corner frequency is omega c1 is equal to 1 by 0.2, 1 by 0.2 is 5. This 1 plus j 0.2 omega is in the numerator, slope is plus 220. So adding minus 20 with the plus 20, the change in slope is 0 decibels. Then the last parameter is denominator part 1 divided by 1 minus 0.01 omega square plus 0.16 omega. So for this, omega c2 is equal to 10. Corner frequency is 10. So that is slope is, since it is there in the denominator, it is minus 40. Minus 40, so 0 with the 0 add minus 40, you are getting a slope as minus 40. Choose a lower frequency omega n such that omega 1 is less than omega c1, and choose a higher frequency omega h is greater than omega c2. So I'll take it as omega l is equal to 0.5 and omega h is equal to 20 radians per second. Let a is equal to magnitude of g of j omega in decibels. At omega is equal to omega L, A is equal to 20 log 0.75 by j omega is equal to 20 log 0.75 divided by 0.5 is equal to 3.5 decibels. At omega is equal to omega C1, A value is minus 16.5 decibels. At omega is equal to omega C2, it is minus 16.5 decibels. At omega is equal to omega H, the value is minus 28.5 decibels. Phase plot. Phase angle of g of j omega as a function of omega is given by phase of g of j omega is equal to tan inverse of 0.2 omega minus 90 degree minus tan inverse of 0.16 omega divided by 1 minus 0.01 omega square for omega less than or equal to omega n. So then tan inverse of 0.2 omega minus 90 minus tan inverse of 0.16 omega divided by 1 minus 0.01 omega square plus 180 degree for omega greater than omega n. So we'll taking the values for in radians, omega is 0.5 to 100. In between range values we'll take, and we'll calculate the corresponding values. And so for degree phi angle in degrees, it is for when it is omega is equal to 0.5, it is minus 88 degrees. When it is 1, minus 88 degrees. When it is omega is equal to 5, it is minus 92 degrees. 10, it is minus 116 degrees. 20, minus 148 degrees. 50, minus 168 degrees. When omega is equal to 100, it is minus 174. So same points, we are marking both the phase magnitude part and place part in the same graph. So we'll take the second example. Plot the Bode diagram for the following transfer function and obtain gain and the phase crossover frequencies. G of s is equal to 10 divided by s into 1 plus 0.4s and 1 plus 0.1s. The sinusoidal transfer function of g of j omega is obtained by replacing j omega in the transfer function. 10 divided by j omega 1 plus j zero point 0.4 omega 1 plus j 0.1 omega. Magnitude per so corner frequencies are omega c is equal to 1 by 0.4, that is 2.5 radians per second, and omega c2 is equal to 1 by 0.1, it is 10 radians per second. So first term is 10 by j omega, no corner frequency, slope is minus 20, so no change of slope. So next term is 1 by 1 plus j 0.4 omega, omega c1 is equal to 1 by 0.4, that is 2.5. This is the term is there in the denominator, the slope will be minus 20. Adding this slope with the above slope, that is minus 20 minus 20, it is minus 40 decibels. Then the next term is 1 divided by 1 plus j 0.1 omega, that is corner frequency is 1 divided by 0.1, that is equal to 10. So since the term is there in the denominator, the slope is minus 20. So minus 40 minus 20, it is minus 60. So choose a lower frequency omega L such that omega L should be less than omega C1, and choose a higher frequency omega H such that omega H is greater than omega C2. Let omega L is equal to 0.1 radians per second and omega H is equal to 50 radians per second. Let A is equal to magnitude of G of j omega in decibels. At omega is equal to omega L, A is 40 decibels. At omega is equal to omega C1, A is 12 decibels. At omega is equal to omega C2, A value is minus 12 dB. At omega is equal to omega H, A value is minus 54 decibels. So phase angle, so phi is minus 90 degree minus tan inverse of 0.4 omega minus tan inverse of 0.1 omega. So for omega is equal to 0.1, phi value will be minus 92 degrees. When it is 1, minus 118. When it is 2.5, it is minus 150 degrees. When omega is 4, minus 170 degree. When omega is 10, it is minus 210 degree. When omega is 20, it is 236. So both magnitude and the phase plot drawn in the same semi-log sheet. So by the graph, we can result that the gain crossover frequency will get 5 radians per second and phase crossover frequency is 5 radians per second.